All right, we are looking at section 8.1 today, integration by parts. 8.1, integration by parts. Integration by parts is just going to give us another tool to put in our arsenal for integration. For instance, if you look at example number 1, we have the integration of a product. The only way that we know how to integrate a product is by using U substitution. But U substitution isn't going to do me any good here. If I let U be equal to sine, the derivative of that is cosine. I don't have a cosine. And if I let U be equal to x, the derivative of x is going to be 1, so the differential would be dx. So that doesn't do me any good. That just gives me U du, and I'm still stuck with this sign in here. So I don't have any way of integrating this as we stand now. I need an additional method for integrating a product. And so that's what integration by parts is going to give us. Because we know the derivative of a product is first times derivative of second plus second times derivative of first. If we integrate the derivative, we go back to the original, right? So let's do that. Let's take the answer that we got when we took the derivative. We'll pull it down here, and when we integrate that derivative, we should go back to the original product, f of x, g of x. So the integration of first times derivative of second plus second times derivative of first is going to be that original product. Now, just so that we can keep up with this a little easier, I've kind of color-coded the different pieces of what we've got right now. So we've got one piece in red, one piece in green, and one piece in blue. All right. This is the integration of two separate pieces that are being added. So of course I can break that into two separate integrals that are being added, still equal to that same product. If I take this second integral and I subtract it over to the other side, so I'm taking that green piece and moving it over to the right hand side, then that'll give us the formula that we see here. That is our formula for integration by parts that they give us in our textbook. Now, that's a little lengthy to keep up with, and so a simpler version of that, and the one that we will refer to when we're using integration by parts, is the integration of u dv is equal to uv minus the integration of v du. And all that we're doing there is, instead of having f of x and g of x, we're going to have u and dv. I'm sorry, u and v. So the idea is, if I come over here and I call f of x u and I call g of x v, then this would be the integration of u times the derivative of v. That's what you see right here. And that would be equal to original function u times original function v. So that's right here, uv minus the integration of original function v derivative of u. So v du. So just a little more concise way if we replace f of x with u and if we replace g of x with v. All right, so now let's retry example number 1 and see if that helps us. I could go through, I've got a product, so I'm going to call one of these u and I'm going to call one of these dv, because again, in my integration by parts, I need a u and a dv. So I'm going to call this u and I'm going to call this dv. So u is x and dv is sine x dx. All right? So if I have u, if I notice in my formula, in order to accomplish this, I'm going to need to know what du is, and I'm going to need to know what v is. Because if you'll notice down here, I'm going to have to fill those parts in. I've got to fill in du here, v here, v here. So since I know u, I could find the derivative of u. So the derivative of x would just be 1. And so the differential du would be 1 dx. Since I know dv, that's the derivative of v, to go back to just plain v, I need to integrate. So let's integrate our sine x dx. And when we integrate sine x dx, we'll end up with negative cosine x. So now we can use our formula. And we can say, okay, if u is equal to x and v is negative cosine x, then we can say u is x, v is negative cosine x. Minus the integration of v is negative cosine x, and du was dx. So just following our formula there, u, v, minus the integration of v du. Now, here's what we accomplished. When we started this problem, we had the integration of a product. Now, we just have the integration of a singular quantity, negative cosine x. So integration by parts gives us a way to simplify our integrand into something that we can do. So let's simplify a little bit here. We've got x times negative cosine x, so that'll be negative x cosine x. Minus a negative is going to give us plus the integration of cosine x. And integration of cosine would just give us sine. Because this was indefinite integration, we also want to be sure to include our arbitrary constant at the end, the plus c. All right, when we started this problem, we chose u to be x and dv to be sine x dx. How did I know to do that? I mean, what if I had chosen the opposite? You can multiply in any order. I mean, 2 times 3 is the same thing as 3 times 2. So what if on that initial problem, instead of letting the first piece be u and the second piece be dv, what if I had reversed them? What if I had let u be sine x and dv be x dx? All right, well, let's look at it. U is sine x and dv is x dx. Because it doesn't matter which order that I put it in. It may be that one is simpler than the other. So again, in order to complete my formula, I'm going to need du and I'm going to need v. So let's find du. The derivative of sine is cosine, so the differential du would be cosine x dx. And if dv is x dx, then to go undo the derivative of v and go to just plain v, I would need to integrate. So if we integrate x dx, then we're going to end up with 1/2 x squared. So now I have all the pieces that I need to follow my formula. So if I come down and follow my formula, u was equal to sine, v was 1/2 x squared. Minus the integration of v was equal to 1/2 x squared, du was cosine x dx. All right, now hang on for just a second. When we started this problem, example number 1, we had x to the first times a trig function. Now I have x to the second times the trig function. I didn't make this better. I made this worse. So that's how I can determine what I want to choose for u and what I want to choose for dv out of my integrand. Here's one way to think about it. If one of the pieces gets simpler by either deriving it or integrating it, that helps me narrow down which way I want to go. For instance, in this problem, if you take the derivative of a trig function or you integrate a trig function, you have basically the same idea. The derivative of sine is cosine. The integration of sine is going to give us negative cosine. So it's about the same level of difficulty. However, if you integrate x or you take the derivative of x, it makes a big difference, right? Because if you take the derivative of x, you get 1. If you integrate x, you get 1/2 x squared. So 1 definitely will make my integrand simpler, and 1 definitely will make my integrand more complicated. So if I'll stop and think about it for just a moment, I might be able to save myself some time and effort. So in the textbook, they tell us that really it's a little bit of trial and error. If you try it the first time and it doesn't work, you might try switching your u and your dv and try something different. you absolutely can do that, but if you think about it a little bit first, you might be able to determine what's the best way to go without needing to try several different ways. Let's look at another one. Look at example 3. For example number 3, I have x squared and I have e to the x dx. So if I'm looking at that and I'm trying to figure out, do I want u to be x squared or do I want u to be e to the x? Do I want dv to be x squared dx or do I want dv to be e to the x dx? Well, the derivative of e to the x and the integral of e to the x are just e to the x, right? However, the derivative of x squared gets simpler. The integration of x squared gets more complicated. So I definitely want to take the derivative of x squared. That means that I need u to be x squared if I'm going to find its differential. And so the derivative of x squared is 2x. The differential du would be 2x dx. That means e to the x dx is going to be dv. And so to get rid of that derivative and go back to plain v, I'm going to integrate both sides. Integration of e to the x is just e to the x. So now I have all the pieces that I need that I can use my integration by parts formula. So we can say, okay, if u is x squared and v is e to the x, u is x squared, v is e to the x, minus the integration of v du, minus the integration of v is e to the x, du is 2x dx. So e to the x, we could pull that constant 2 out in front, 2x dx. Now you look at that and you're like, well, hang on, I still have a product. I still can't do that problem. You're right, but I'm making progress, right? It's better than what I started with. I started with x to the second times e to the x. Now I have x to the first times e to the x. So there are times that I may just need to do integration by parts more than once. So I'm going to start over only with my integrand. Notice that all of this is already taken care of. Let's just bring it straight down. So x squared e to the x minus 2 will bring straight down. And let's focus on this new integrand e to the x, x dx. Again, if I take the derivative of e to the x or integrate it, it doesn't change. But if I take the derivative of x, it gets simpler. If I integrate it, it gets more complicated. So I'm going to let u be equal to x so that I can take the derivative of it. The derivative of x would be 1, so the differential du would be 1 dx. That leaves e to the x dx for dv. Integrate that to get v, and I have e to the x. So now I'm going to follow my integration by parts formula. Again, we're just going to bring this first part straight down. Over here, u was x, and v was e to the x. So x e to the x. Minus the integration of v du. So v e to the x du dx will give us integration of e to the x dx. Now we have an integrand that will be simple and straightforward to work with. So integration of e to the x is just going to give us e to the x. So we want to distribute this negative 2 all the way through here. So that's going to give us negative 2x to the ex, negative 2x to the ex. Then remember this integration was e to the x. So if we distribute that negative 2 times the negative is going to give us positive 2 e to the x. We also, when we integrated here, got an arbitrary constant of plus c, so we actually have negative 2 times plus c. If you take negative 2 times a constant, you still get that constant. But in the textbook, they also show you another way that you could note that, where you could say, okay, if I have negative 2 times my constant, let me call that the constant with a subscript of 1. So c sub 1 could be used to replace negative 2 times c. All right, let's look at example 5. In example 5, we have a definite integral using integration by parts. So here's our same formula that we started the day with. All that we've changed is that if you have upper and lower limits of integration a and b, then you're also going to have them in the first piece of your answer and also in that simplified integral that you're working. And here it is if we would rather write it with the uv. We've still got integration by parts is uv minus the integration of v du. And again, the only thing that we're adding is just the upper and lower limits of integration. Now, this one was a little more involved, so I filled it in for you there on your note sheet. But for example number 5, we have the integration of inverse tangent x from 0 to 1. So when I first look at this, I may not notice that I have a product. If I don't have a formula for inverse tangent or whatever it might be that I'm working with for my integrand, I could let this be u and I could let dx be dv. There's no way to take the derivative of dx, so with integration by parts I don't have a choice. I'm going to have to integrate the dx and take the derivative of this other piece. So let's let u be equal to inverse tangent, and let's let dv be equal to dx. So if I take the derivative of inverse tangent, and that's going to give me 1 over 1 plus x squared, so the differential du would be 1 over 1 plus x squared times dx. So we could put that dx in the numerator if we wanted to. To find my v value, I'm going to have to integrate dv to go back to the original function to get rid of that derivative. So if I integrate dx, I'm just going to get x. So now I can come down and use my formula. So u was inverse tangent, v was x, from 0 to 1. Now notice that 0 and 1 didn't change. I haven't done u substitution as I typically would think of substitution, so I'm not having to change my upper and lower limits here. Minus the integration of v, and v was x, du is dx over 1 plus x squared. All right, let's focus on this first part for a second. If I go through and I plug in 1, I'm going to have 1 times the inverse tangent of 1, so 1 times the inverse tangent of 1, minus, plug in my 0, 0 times the inverse tangent of 0. So 0 times the inverse tangent of 0. Here's that same integral that we had a second ago. We're just bringing it along. We'll work on it in a second. So inverse tangent of 1, we're saying where does tangent equal to 1, and I only have first and fourth quadrants to choose from. Tangent is equal to 1 at pi over 4. That's my reference angle. And since this was a positive 1, then I have to be in the first quadrant. If it had been a negative 1, I would have been in the fourth quadrant. So the first quadrant with a reference angle of pi over 4 is just going to give us pi over 4. Inverse tangent of 0, we're saying where is tangent equal to 0, and I only have first and fourth quadrants to choose from. Values between negative pi over 2 and positive pi over 2, not including negative 2 and positive pi over 2. So if you think about tangent as sine over cosine, at 0, sine is 0 and cosine is 1, so 0 divided by 1 would give me 0. That's the only place that tangent is equal to 0 within that interval negative pi over 2 to positive pi over 2. So this is going to be 0. So I'll have pi over 4 minus 0 minus this integrand. So pi over 4 minus 0 would just give us 0 minus my integration here. All right, so now I have a different problem. I have a quotient. I don't have a rule for quotients, so I'm going to try and use our u substitution from section 5.5. Now, because we've already got u's and v's going on up here, instead of calling it u substitution like we typically do, I'm just going to use a different variable. But the same idea, I'm going to go through and say, I'm going to let this quantity in my denominator be what I substitute out. So t would be 1 plus x squared. So the derivative of that would be 2x, and the differential would be 2x dx. Then I just had an x dx, so I'm going to have to get rid of the 2. So divide both sides by 2, and 1/2 dt will be x dx. So I'm going to replace this x dx right here with the 1/2 dt. This whole denominator became t, so we've got our t in the denominator. And if we replace these x's with t's, I also need to replace my upper and lower limits of integration with t's. So I can say, okay, when x is equal to 0, then 1 plus 0 squared is going to give me 1 for t. And when x is equal to 1, then 1 plus 1 squared is going to give me 2 for t. So we're going to integrate from 1 to 2. All right, so integration of 1 over t is just ln absolute value of t. So we have that here, ln absolute value of t, and that constant of 1/2 out in front. Plug in our 2 and plug in our 1 and subtract. So now I've got pi over 4 minus 1/2 ln 2 minus 1/2 ln 1. So pi over 2 minus 1/2 ln 2 minus 1/2. ln of 1 is 0. So that piece is going to drop out, and we'll have pi over 4 minus ln 2 over 2. Want to give the exact value unless they tell us to give a decimal approximation. All right, so here is our homework for tonight. On pages 508 to 509, we're doing 1 through 21, every other odd. Challenge 41, omit number 13.